Okay, so for this first one, they give you the graph of some function, and they ask you which of the following could be the graph of the second derivative. Okay, so first thing, look at the original and see that it's originally concave down. This is concave down here. And just kind of barely concave down. It doesn't have much, it's not like super curved, so kind of barely concave down. So at least to start with, the second derivative will be negative. Concave down means second derivative negative. So that means it's either A or C. Cross those out. And then it's hard to tell exactly, but here it looks like the concavity is kind of nothing. It doesn't look concave up or down. And so I don't think it's C, because this goes above, the second derivative goes above the x-axis, so it looks like that would mean that the function's concave up, but it doesn't look concave up, so it looks more like A. But it's a close one between those two. Okay, so they give us three graphs, and each one is kind of the derivative of another one. Or two are the derivative of the other two. Okay, so you just kind of have to kind of check out slopes. The slope of one will be like the values of another. So, and just kind of look. So do you see? Focus on like where one of them is increasing and decreasing. So you can see the third one's decreasing from 0 until about 1.5. So if the graph of the derivative of this should be negative from 0 to 1.5. And that's what this is. This is below the x-axis from 0 to 1.5. And then here from like 1.5 to 2, this is increasing. And then this is above the x-axis. So this looks like it's going to be it. So from 2 to 2.5, it's decreasing. That's what this says, 2 to 2.5 below the x-axis. From 2.5 to 4, it's increasing. From 2.5 to 4, it's above. And then from 4 on, at least in this graph, it's decreasing. And from 4 on, it looks like it's below the x-axis. Okay, so definitely 2 is the derivative of 3. Okay, so wait. Yeah, 2 is the derivative of 3. All right, and then let's look at the answer choices to help us. Oh, so it's got to be D. And then let's just check out. So D is the only one where 2 is the derivative of, we have like 2 is the derivative of 3. So let's see if 1 is the derivative of 2. So let's check it out just to make sure. Okay, if 1 is the derivative of 2, we'll focus on 2. So we see this is increasing from 0 to 1.5. And this is above the x. Actually, it's increasing from 0, to 1.5, and then keeps increasing all the way until you get to 3. And that makes sense. And there's discontinuity here. So discontinuity here, that makes sense. So this is above the x-axis until 4. And this is increasing until 4. And then this is decreasing until from 3 to, or sorry, 1, 2, 3. I don't know. Decreasing from 3 to, 5. And then below the x-axis from 3 to 5. Yeah, so that checks out. So it's got to be D. Okay, so figure above shows a graph of f on the interval AB. Which of the following could be the graph of f prime? All right, so we're just looking at slopes. Here, let me get all these. Okay, so the function's increasing up until a little past 0. So the derivative should be positive up until 0. So we can eliminate that. And that's it. Okay. Then the function a little past 0 to here is decreasing. So the derivative should be below the x-axis for just a little bit. Looks like it's going to be b. Definitely not d. Yeah, since this, if this was the derivative, and this is below the x-axis, all the way to b, from here to b, this function would be decreasing the whole time, but it's not. Decreasing, increasing, decreasing. So, okay, so yeah, so decreasing here, below the x-axis here, below the x-axis here. Okay, then this starts increasing. So the derivative should be above the x-axis. This little stretch, that's like this little stretch or this little stretch. Okay, and then it's decreasing. So this should be below the x-axis. So it's really between b and c, and it's kind of a close one. But I think it's going to be b because here, these two parts of this derivative, they don't go very low. So this is saying that here, this little stretch means the slopes are negative of the regular function, but not very negative. But you can see like here, like this stretch, it gets to be somewhat negative, maybe. Yeah, it's kind of a close one. Wait, let's look at something, anything else. Okay, so I think it's going to be b, because you can see actually what kind of tipped me off, like this first part. So this is increasing pretty heavily, like, yeah, this is increasing a lot, kind of steadily, a big slope, all this stretch. Yeah, and then it's so tough to tell, but like this looks like it kind of starts to, the slope kind of is going to 0, getting close to 0, and that's like what this is. Like here the slope is positive, but the slope of the tangent line is kind of, looks like this is kind of curving maybe, and that this slope would be close to 0, just a little bit above the x-axis. Yeah, hard to tell though, but I think it's going to be a b. Okay, so acceleration in meters per second of a race car is modeled by that function. Okay, so that's an acceleration function. And then they ask what's the car's maximum acceleration on the time interval from 0 to 6. Okay, if you have a function for acceleration and you're trying to maximize acceleration. So that's exactly what optimization is. So you have a function that you're trying to optimize that function. So all you do is take the derivative of that function. Okay, and then we'll set it equal to 0. Okay, and then we get 2 critical points from this. All right, and then just off to the side, we'll plug in the endpoints. So they have this interval from 0 to 6. So we'll plug in into the original, into A of t. So we'll plug in 0, plug in 6. So plug in the two endpoints, and then we'll plug in also the critical points we found. Okay, and so now we're just testing. We know that the maximum value is going to be at an endpoint or a critical point, so we'll just plug all these in and see which one's the biggest to get the max. Okay, so plug in 0, you get 10 for sure. Here I'm going to do the rest in the calculator. Okay, so for the rest, at 6 it was 28, 2 it's 12, and at 3 it's 5.5. Okay, so now we know this is the maximum. Okay, so the maximum acceleration is 28, and it happens when t is 6. And so that's d. And t equals 6. Okay, this one, if you haven't seen one like this, I won't put one like this on the test because I feel like it kind of requires you to see a problem like this before. So they say the total cost in dollars to order X units of a certain product is modeled by that function. So that's a cost function, to cost to order a certain amount of units. Okay, and then they ask, according to the model, for what size order is the cost per unit a minimum? Okay, so this function is not the cost per unit, right? So this function is not what we're trying to minimize. So we need to get a cost per unit function, some function that represents cost per unit, and then we'll take the find the minimum of that, and that means taking the derivative of that. Okay, so if the cost is that, and x is the number of units, then the cost per unit is just dividing by x. So I'll call this function p, cost per unit. Just divide everything by x, like this. Okay, so now that is the cost per unit, just dividing by x. So cost divided by x, number of units, cost per unit. All right, so this is what we'll take derivative of. And then keep in mind this function, and y'all are good at this, I think, but or just that 30 or 320, that's 320 x negative 1. Okay, so we'll set this equal to 0. So we get x squared equals 320 over 5, which is 64. Okay, and technically x equals plus or minus 8, but you can't have negative units, so we'll just really x equals 8. Okay, remember from all that work that we did, we could actually test it. We could maybe do a number line test to make sure it's an actual minimum and not a maximum. But we know that this is going to be it, so it's always one of the critical points. Okay, so it's going to be B. Order of 8 units has a minimum cost per unit. Okay, so ultimately they asking about minimum cost. So right when you see they're asking about minimum or maximum of some, besides just a random function, if you have context, then this is kind of like an optimization problem, or is an optimization problem. Okay, so to start this one, okay, so we want to minimize Wait, sorry. 5,000. It's $5,000 per mile to install electrical line on land and 10,000 underwater. So it's like there's going to be a certain here. So we're going to run a line, and you could run it along the land for a little bit and then run a certain amount through the water, or you could do it like all through the water, or it could be almost all through the land and then to water. So we're just going to try to figure out which one's the best, or what's the best way to do this. Okay, so it's going to be something like this. I'm going to just pick a random spot, so just like that, and then like that. Okay, so the price in land is 5,000, and the other one is sorry. Okay, yeah. So here. So look at all these equations. So do you see there's 5,000x to all of them? And so it makes sense to call the line that's being run on land, call that distance x. Here. And then 5,000x will be the cost of running this line on land. Okay. And then for now, call this y, and that'll be the amount of line that's run through the underwater. Then that'll be $10,000. Okay, so the cost we know is 5,000x plus 10,000y. Okay, but we want to get this all in terms of x. All the answer choices. So that y, we want to substitute, find an equation with y and then substitute it in. Okay, so probably we can focus on this triangle. Kind of look at this as like a right triangle here. And then think about if this whole thing is 4 and this is x, then this little bit is 4 minus x. Okay, and then this bottom is 1, so I'm going to kind of draw this off to the side just to get it out of there. Okay, so we'll definitely do Pythagorean theorem. And then we can square root everything. Okay, and then we can take this and substitute it in for y. Can we see which one it is? Oh yeah. So it's either going to be a or b. Okay, so those are the right cost functions. So let's see. So they say solve c prime is 0. So that's both those, and that's what we'll do. And find values where c prime changes sign from positive to negative. And this one says from negative to positive. Okay. So if we want to find a minimum, then we want to know where the derivative goes from, we want the derivative to go from negative to positive, because the minimum will happen when a function's decreasing, derivative negative, and then increasing, derivative positive. And then that's derivative 0, and that's a min. Okay, so you need a negative. That's where the derivative would be negative. And this is where the derivative would be positive. Okay, and that's what creates a minimum. So this is from negative to positive, so that's going to be b. Okay, so like always, when they ask for horizontal tangents, they want to know when the derivative is 0. So let me rewrite this. Okay, so we're going to, what did I say? What value of x is, yeah, horizontal tangent. So we want to find y prime, and then set that equal to 0, see where it's set that equal to 0 for a horizontal tangent. Okay, so let's do that. So take derivative, and we'll do implicit differentiation. And just so you know, you have a choice, and I'm not sure which way is better, actually. But you could rewrite this as e to the x over e to the y. I don't know. I'd say we just take derivative of this as it is. So that's what I'm going to do. Okay, so derivative of exponential, we'll take derivative of the exponent. So derivative of x is 1, derivative of y is y prime, and then just times that by the exact same thing, just rewritten. Okay, and then we want to solve for y prime, so we'll divide by this. That. Okay, do y'all get we can do this? 2x and then e to the y minus x. Just switch those, and yeah, so you know when something's in the denominator, you can negate the exponent to put it in the numerator, or the other way around. And so negating two things subtracted means switching them. Anyways, okay. So and then just put it over here. Okay, so let's solve this for y prime. Just be 1 minus. Okay, and they say, at what value of x does the curve have a horizontal tangent? Okay, so let's see. Okay, actually, let's do this also. So if we look at the original, e to the x minus y is x squared. So if you can kind of like raise both of these to negative exponents. I'll do that over to the side. Actually, I'll do that up here. So you have x squared to the negative 1. That's y to the negative 1, just some algebra. So this will be multiply exponents. This will be x negative 2. And then when you multiply those, you get e to the y minus x. You can switch those. Okay, so I'm going to substitute that to get this all in terms of x, since they're only asking about the x coordinate. Like that. Okay, so that is what we'll set equal to 0 and solve for x. Okay, so let me do that up here. Okay, so that'll end up simplifying to be 2 over x. And can you just see x, if x is 2, that works. Okay, and that's it. All right, so they tell you a curve in the xy plane is defined by some equation, which of the following statements are true. And then we just look at all these. They're giving you kind of, the first two are giving you kind of specific values of x or y, where they're telling you that there might be a horizontal tangent or a vertical tangent. And then the last one, and so those both deal with derivatives, you know, horizontal tangents or vertical tangents, any kind of tangents. And the last one, line tangent to the curve, has slope of 1/2. That's derivative also. Okay, so let's take derivative of this equation. Okay, so take derivative. Okay, and then, I don't know, maybe we solve this for y prime. Okay, let's do that. Okay, so the two terms with y prime will keep on, left-hand side. Okay, the other two terms bring over to the other side. Okay, and then basically we'll factor out the y prime and then divide by what's left. So you just get this. Okay. The fact that this is in terms of x and y. Oh, actually, well, okay. Actually, now that I think about it, so they say the point at which x equals -2, there's the tangent's horizontal. That's actually true. So you can see the top, since we're dealing with a fraction, this whole thing is 0 when the top is 0. And you can see when x is -2, the top is 0. So that is a horizontal tangent. Okay, so the first one checks out. Okay, next one, point when y equals -8, lines are vertical. So you can see when y is -8, the bottom of this fraction is 0, and that corresponds to a vertical tangent. When the bottom is 0, then you kind of have like an infinite slope, and vertical tangents have infinite slopes. So that one's true also. Okay, and then the line tangent to the curve of the point -1, 1 has slope a half. So here we'll just plug in -1 and 1. I'll get this notation, -1, 1. So remember, anytime you have an expression, vertical line, and then either a point or x equals something or y equals something, it just tells you that you're about to plug that, whatever's here, you're going to plug in here. Okay, that just ends up being 3, and then plug in 1 for y, 18, and this is a half, like they say. So all 3 of these are true. Whoops. All right, so this gives you a function, kind of mixed with x and y, so we'll have to take derivative implicitly. They asked how many horizontal and vertical tangents it has. Okay, so first we'll take derivative. So we'll have to do a product rule for this and product rule for this also. Okay, so derivative of x is just 1, and then 1 times y squared, x times derivative of y squared. Derivative 2 is 0, and so we'll just do product rule. So derivative of x is 1 times y is just y, plus x times derivative of y. All right, and then I'm going to bring this term to the left and this term to the right. And then I'll kind of rewrite this. Okay, so just factor out a y prime and divide it by what was left. Wait, what am I doing? Oh, this should be y squared. Yeah, it's a y squared there. All right, what are we doing? Oh, how many? Okay, so we're going to get a horizontal tangent at any points when the top of this fraction is 0, and a vertical tangent at any points when the bottom is 0. All right, so we'll set the top equal to 0. Okay, and so when y is either 0 or 1, then we'll have a horizontal tangent. Okay, so it looks like there's 2 right now, but maybe there's some reason why there's not. Okay. Okay, so let's take let's set the bottom equal to 0. See what happens. Okay, so when either x equals 0, there's a vertical. When y equals 1/2, there's a vertical. Okay, so let's see. Hold on. Okay, and this one's kind of tricky actually. So you see from the first one we got y equals 0 and y equals 1. So y equals 0 is no good because if you look back in the original, there's no point on this curve where y equals 0. So if you plug in 0 for both these y's, you get 0 equals 2, and so that's not true, so there is no point that has 0 as a y coordinate. Same thing with x. If you plug in 0 for these two x's in the original, you get 0 equals 2, so x equals 0 can't be a value. If we plug in 1 for y, then there are values of x that work. If you plug in 1 for y, you get, oh wait, let's see. If you plug in 1 for y, you get x equals 2 plus x, and actually that can't happen either. So there's no, so y can't be 1. Let me make sure about that. Yeah, so that's actually kind of tricky. Okay, and last thing, if y is a half, so let's see, if y is a half, you get 1/4 x equals 2 plus 1/2 x. And then there are values of x that we could solve that for x. So there, all right, so that means, yeah, y equals a half was something that made a vertical tangent. So there's one vertical, but no horizontal. All right, so that one's kind of tricky. All right, this one says, let the curve, or let C be the curve defined by that equation. Consider all points x, y on the curve C where y is positive. Which of the following statements provides a justification for the concavity of the curve? Okay. Sorry, just looking at the answer choices. Okay. So they're all just kind of given examples of y double prime, and there's, yeah, so really all the y double primes are different, so we really just have to find y double prime and see which one it is. Okay, so we'll take derivative. Okay, I'm going to divide by, actually let's just solve for y prime. Okay, and then it's really going to be x over y because the 2's will cancel. Okay, so now we'll take the derivative of that. Do quotient rule. Actually, I'll put this negative out front, I guess. Yeah. Okay, so just be careful. There's a negative there. Okay, derivative of the top times the bottom minus top times derivative of the bottom all over bottom squared. All right, and then y prime, this is y prime, so we'll plug it in for y prime there. Okay, since this is minus and that's negative, this will become plus. And it's really going to be x squared over y. All right, and then a little tip. You want to get rid of, there's only one denominator. That's, it is a complex fraction where you have a fraction within a fraction. I also call them extended fractions. But one thing, since there's only one denominator besides, within the fraction, just times top and bottom by this denominator. And so you can see, like, if you times this top by y, times the bottom by y, Okay, and that kind of cleans it up a little bit. Okay, and then they're being tricky again. So notice this is not an answer choice, right? You have y cubed in the bottom in a couple of these, but you don't have this x squared plus y squared in the top. But notice that x squared plus y squared equals 36. So we could rewrite this. Just substitute 36. All right, and then now that becomes c, and it is concave down because this is always negative, and this whole thing's always negative because that y is always positive, and you have a negative out front here. And so it's got to be c for a few different reasons, a couple of reasons. Okay, so this gives you, it tells you about there's a point on some curve. Which of the following statements is true about the curve at that point? And all the answer choices are just saying whether the derivative and second derivative are positive or negative. And so that's all we care about. Is the first derivative positive or negative? Is the second derivative positive or negative? Okay, so we'll try this, do this as easy as we can. Okay, let me rewrite this. X squared y cubed. Okay, so we'll take derivative, product rule. So derivative of the first times second plus first times derivative of the second. Okay, let's solve that for y prime. Okay, and then let's clean this up a little bit. The x and x squared cancel. Here we have a 2. And then there'll just be an x in the bottom and a y in the top. Okay, and then we can see for this point, if you plug in -3 and 4 for x and y, the fraction becomes negative, but then this negative out front makes it positive. So that's going to be positive, the first derivative. So we'll cancel those out. Okay, so let's take derivative again. Okay, I'll take derivative of that. So we'll do quotient rule. Okay, derivative of the top times the bottom minus top times the derivative of the bottom all over the bottom squared. Okay, we could clean this up actually just a little bit. Okay, I'm going to apply this negative to the top, and that switches these. So yeah, these two things in the top will just switch. So that this will be 6y, that'll come first. And then this 6xy prime. All right, so you could substitute this y prime for this, but we already know for that point, we already know that this is some positive number, and that's the only thing that really matters, I think. Actually, maybe not. Okay, actually, let's figure what it is. Okay, so if we evaluate this at the point -3, 4. Okay, so plug in y, the top is 8. Plug in x, the bottom is -9. So this is 8 over 9. Okay, so let's plug this point in. And then when we come to the derivative, this y prime, we'll plug in 8 over 9. Oops. Okay, 6y is 4. The only thing we care about is if this is positive or negative. So this will definitely be positive because this negative and this negative cancel. So everything in the top is positive and added. And then the bottom is positive since that's squared. So second derivative positive. And so that is D. Both positive. Okay, so this one talks about there's a point on a curve, I think some given point. They give you the derivative, dy dx is 4x over 9y. Which of the following statements is true? Okay, and then all of them talk about at the same point, at the point 0, negative 2. Is there relative max or min? And then what's the reason? So let's look if we can eliminate some just because the reason doesn't make sense. Okay, first off, they talk about there's a relative minimum because the derivative is 0 and the second derivative is positive. Okay, if the second derivative was positive, then this would be concave up and you would have a minimum value. So that checks out. Okay, the next one says there's a relative minimum because the derivative is 0. So all these talk about the derivative is 0, so that's fine. Relative minimum because the second derivative is negative. No, that doesn't make sense. If the second derivative was negative, this would be concave down, and this would be a max. So that doesn't even make sense. And we don't really have to do this, but just to kind of learn from it. Okay, next one says there's a relative maximum because the second derivative is positive. No, we can see second derivative positive means minimum. So that one doesn't make sense. All right, and then the last one does make sense, relative max, because second derivative negative, there is a max there. All right, so let's just find, so really we just want to see is the second derivative positive or negative. Okay, so we've got the first derivative there. I'm going to rewrite that as y prime. And then we'll take second derivative now. Okay, so derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. Make sure that's right. Top times the derivative of the top times bottom minus top times, yeah, okay. Okay, and then at 0, 2, you can see the derivative is 0. When you plug in 0 for x, the derivative is 0. So that means this y prime at that point is 0. So this whole thing just goes away, that whole term. Okay, and then all we're left with is y's. So we'll plug in -2 for those two y's. So technically we're plugging in the whole point, but there's no more x's, so we're just plugging in the y's. Okay, so that'll be, okay, so we can see the top's going to be negative because we're going to plug in a -2. That's going to make this negative, and the bottom's always positive. So the second derivative ends up being negative. So that is answer choice D. All right, that's it.